Hey everybody, esi-lag or multi-chassis link aggregation group. What a technology this actually is, and in this video I'm going to be going through whether or not you should even consider and what my thoughts are on the esi-lag technology. Hey everybody and welcome back. If it's your first time here, welcome to this channel. I'm David Townsend. This is the Net Academy where we are learning networks together. And as I said, this whole video is about esi-lag or multi-chassis link aggregation group. Again, another big acronym in the technology world. But this is a technology that is not new. It has been around for quite a long time. And as far as I'm aware, it is implemented across quite a few different vendors, Juniper, Aruba, Cisco, so on and so forth. So it is by far not new. And esi-lag as a technology does have its complexities, just like any other protocol and any other technology. And the whole purpose of this video is for me to introduce what esi-lag, multi-chassis link aggregation group, I'm just going to call it esi-lag for short moving forward. But I'm just going to be going through what esi-lag is, what benefits does it bring, what do you need to be aware of, and of course how to configure esi-lag in a Juniper Junos environment. And that will be towards the end of this video. But right at the end of this video, I'm going to really answer that question: to esi-lag or to not esi-lag. I'm going to answer that right at the end, but you are 100% going to see me becoming a certain way when I go through the configuration on Junos, because as I said, esi-lag is quite complex and there are quite a few attributes that have to match between different esi-lag peers and attributes that do not have to match between different esi-lag peers. And if you get it wrong, esi-lag just generally does not work. So it's complicated. But first, let's start off with the theory. Just a few friendly bullet point slides, nothing too intense, don't worry. And then we'll go into Junos and then finish off on my thoughts on esi-lag. Let's go first with the theory. Okay, so let's start off with the theory. We all know by now what esi-lag actually stands for. Nothing really new or complex there. But when you look at esi-lag as a technology and what it's actually trying to achieve, it's trying to achieve redundancy. It's trying to achieve resiliency in the network when you've got a downstream switch or a downstream tenant or client that is dual NICed. It has dual interfaces to connect into the network for resiliency and redundancy purposes. But without technologies like esi-lag, if you've got a dual NICed, a dual capable server, switch or client that has dual capabilities to connect into the network into two different switches, that can create problems that I'm going to discuss in just a few seconds. So esi-lag was created to address those problems. What esi-lag basically is it allows two or more independent and logically physically separated switches to appear as the same logical device, the same logical switch on the network. So when you've got that dual homed, that dual NIC capable switch, server, client, tenant, whatever, connecting into the network, it sees that upstream I'm connected to the same switch. In reality, it's not. It's connected to two physically separated switches, but esi-lag tricks that end device into thinking that it is. And this is actually the lab that we're going to be going through in EVE-NG in Junos in a few minutes time. But we can actually see here that we've got MCP1 or multi-chassis peer 1 and MC peer 2. And we can also see they're connected to access switch 2 and at the top access switch 1. So without esi-lag, both of these access switches would think that and know that they're connected to two separate physical switches, and that is actually the case. But with esi-lag, they appear as the same logical upstream device. And as such, it brings benefits such as load balancing. So those access switches or clients or tenants, whatever's connecting to these esi-lag peers, they can load balance. They hash traffic they've received and they load balance it via some hashing algorithm to send the traffic upstream to what they think is the same logical device, but they might send some traffic to MCP 1 and another set of traffic to MCP 2, so it allows load balancing. It also prevents any loops being created. And this is a very big important point, because if we look at it from user 1's perspective, it's sending some traffic, whatever the traffic might be, into access switch 1, and access switch 1 without esi-lag would maybe send it to MCP 1 via whatever VLAN, or in this case via VLAN 10. And that would be going to say the destination of user 2 down here with that IP address of 192.168.10.12/24 and also in VLAN 10. Now MCP 1 without esi-lag would see, you want to get to this destination. Well, I can get to that destination via here, this interface here, but I can also get to that destination via here as well. So we really get an inefficient forwarding path just at layer 2. But because initially, in the Ethernet world, no end device really knows who's connected to where, you get that flood and learn approach. MCP 2 would actually broadcast out of all available ports. Is connected to this interface, connected to this port. Do you have this MAC address, i.e. the MAC address of user 2? Obviously it does not. But that's where loop actually creates, is that ARP broadcast. Those ARP requests go round and round and round and round. esi-lag prevents those layer 2 loops. So you don't actually need spanning tree protocol in a network like this. This is just a lab. It's non-production, of course. Always use best practices when deploying any new network and architecture and protocols into a production environment. I'm just saying that there to make it clear. But it does have the benefit of preventing loops. And redundancy. I think this really speaks for itself, because we have this esi-lag peering where these two MC peers appear as one logical upstream. It provides redundancy. So if MCP 1 fails, if this interface goes down, or the device here goes through some kind of hardware maintenance or software upgrades, whatever, Access 1 and Access 2 can still forward traffic to and from MCP 2 and still have connectivity. And as I said at the beginning, it's not a new technology, and it's not too dissimilar from virtual chassis in the aspect that it is providing the same logical upstream from whoever's connecting. So if we look at it from Access 1's perspective, whether it be virtual chassis or esi-lag, Access 1 thinks it's connected to just one upstream device, when in reality, whether it be through virtual chassis or esi-lag in this video, it's connected to 2 or more upstream switches, but logically they appear as one. And esi-lag, I'm going to go through this in, actually it's the next video I'm going to do, but Ethernet segment identifier, link aggregation group. For me, this is lag on steroids. I absolutely love esi-lag and EVPN routing. It is just a great, powerful, scalable protocol, but it's really providing the same kind of benefits to esi-lag and virtual chassis, i.e. redundancy, resiliency, and loop prevention. But guess what? As I said, it is complicated. I'm going to show you in just a minute's time a cheat sheet to use for esi-lag, but I am going to get this wrong in the configuration. I am going to get frustrated, but some things have to match between MC peers and some things absolutely cannot match between MC peers. If you get one attribute, one configuration wrong, esi-lag, the peering, the adjacency, it will not come up. So you have to get it right. Yes, I know you're going to think and say, well, you have to get it right with any protocol. But honestly, esi-lag, there's so many more things that you have to be aware of. And also some things can and cannot match between different MC, multi-chassis, aggregated Ethernet links on the same device. So if you've got multiple MCAE bundles on the same switch, some things have to match and some things cannot match. As I said, it's complicated, but it is also completely proprietary. So if you're looking at doing and implementing esi-lag between Juniper and Aruba, or Aruba and Cisco, or Cisco and Juniper, just for example, it will not work. And that is because esi-lag uses a lot of LACP, or Link Aggregation Control Protocol. And if you know this standard, this is actually defined by 802.3AD. So, and the 802.3 standard really defines the Link Aggregation Control, or LACP protocol. And this is really the control plane on a specific switch. So in this case, MC peer 1 or MC peer 2. It really doesn't define the control plane when interoperating or being communicated between different switches, especially between different vendors. So what Juniper and Arista and Cisco and everyone else came out with to make LACP work, to implement esi-lag, I'm going to go through this, is something called LLCP. And it's really this guy here that makes esi-lag completely proprietary and does not work from one vendor to another vendor. So let's move on to a little bit more detail into how esi-lag actually works. And what you can see now is that between MC peer 1 and MC peer 2, there's probably not good coloring, but right here is an aggregated Ethernet, AE0, and on here is the ICL, or inter-chassis link. Now this is all about data plane forwarding. It is connecting those two or more MC peers together. That's it. It's about data path forwarding between two or more switches. It allows for redundancy during any link failures. So just for example, if access 2 there, the user wants to send traffic to host 1 up here, and just say for example it comes up to MC peer 1, but for whatever reason this link here fails between MCP1 and access 1, it can then forward that data plane traffic over the ICL to MC peer 2, where it goes up to access 1 from there. Now it is recommended to be high speed, and it is recommended to be an aggregated Ethernet. However many links in there, I don't know, 2 or more obviously, but that's really what the ICL actually is. And as I just said, the ICL handles the data forwarding, but now this Inter-Chassis Control Protocol, or ICCP, this is what makes esi-lag completely proprietary. This is interested in the control plane functionality of esi-lag, because in reality MC peer 1 and MC peer 2 are two different switches. They have to appear as the same logical device, and as such certain attributes like ARP and MAC address tables and IGMP snooping has to be synchronized between the different peers, and that is accomplished between or from the ICCP protocol, because this is where the control plane actually happens. Now you can run ICCP over the ICL, so over this link here. You don't really have to do so, and in fact it is also recommended to use an out-of-band management network to run ICCP in case the link here actually does fail, and then you get that dreaded split brain scenario, which you don't want even in a virtual chassis. But really what the ICCP is doing is it's allowing multiple peers to act as a single logical entity to the downstream devices. That's what ICCP is there for. Yes, it brings around the non-proprietary feature set, if you were, of esi-lag, but it's state synchronization. It's allowing those different switches to appear as the same logical device to whatever is connecting to that network. And when it comes to configuring esi-lag and the different attributes, and you're obviously going to see this in just a few minutes time, but there are quite a few different areas that have to be configured. More coming very, very soon. But LACP has to be configured. This is the control plane signaling, really. So LACP has to be configured on the interfaces facing those clients, those dual NIC tenants or switches, i.e. access 1 and access 2 here in this case, that are connecting into the network. We also have to configure the multi-chassis aggregated Ethernet attribute, the system ID, the chassis ID, and another value. There's a lot of different values. They have to be configured. Of course, you need the trunk configuration as well. We need to trunk VLAN 10 across this whole network. Otherwise, it's not going to work for obvious reason. You also have to configure ICCP. ICCP uses layer 3 adjacency. I wouldn't call it adjacency, but connectivity. And as such, you could use an IGP to advertise the IP addressing, which could be a loopback 0 address or an interface address, or maybe an IRB interface, which is what I'm doing in this lab. But you need reachability. ICCP will not work without that reachability. And if ICCP doesn't work, esi-lag 100% will not work. But we also have to configure the ICL. Are you confused yet? I'm trying to make it as simple as possible, but you could see that for such a great technology, I'm using that word loosely, it is complex. I said at the beginning, it is complex. And I thought this would be helpful as a cheat sheet. What has to match and what must not match. So if we look at the service ID, or first what I've done is I've broken it down into, what is it? Does it match or not match? And of course, where is it configured? So let's look at the service ID. Now, in each switch, you could have multiple routing instances. If you're using the default instance on these switches, they have to match. So these have to match between peers. But if you've got another routing instance, let's call it routing instance 1, that will have a different service ID on that switch, and that service ID has to match routing instance 1 on the adjacent switch. So this really identifies the esi-lag domain, that routing instance, and this is configured in the switching options. The session establishment hold time. This is basically an uptime for the ICCP. That has to match. If it doesn't match, then MC, the AE interfaces for MC will stay down. And if you configure it to be too high, it's going to take an incredibly long time for ICCP to become up and established. So this has to match, and that is configured in protocols ICCP. You are going to see this. We also have to be aware of the ICL link, the inter-chassis link that connects the MC peers together. Yes, the link, as I just said, that has to match between peers, and that is configured in multi-chassis, and then you define what the remote IP is. The ICCP VLAN to IRP mapping. Spelling mistake there. That should be protocols, but this is needed for the ICCP reachability. Again, that has to match the VLAN IDs, where we map an MC aggregated Ethernet to a VLAN ID. These have to match between peers, and that's configured in the interface. System ID under LACP, that is also in the interface. That has to match. The admin key. Well, actually, let's go back. What is the system ID? Basically, this identifies to the downstream device. It's a 6-byte value, like a MAC address. What is the upstream device identifier? So access 1 or access 2 will see that same system ID from multiple interfaces, from multiple switches, i.e. esi-lag, and think that it's connected to the same upstream device. So we need the system ID, and that has to match on both MC peer 1 and MC peer 2. There's then the admin key. Now this is not about security. It is not a password. It is used to authenticate the control plane from the MCP peers down to access 1 or to access 2. It must match, and it's in the interface configuration. And then we've got the multi-chassis aggregated Ethernet ID. This is a lot to remember, isn't it? It's a unique identifier that tells Junos, hey, this AE on peer 1 and that AE on peer 2, they're part of the same logical esi-lag. ICP syncs this data. Again, this has to match, and again, that's in the interface configuration. And still moving on, there's more. Anycast IP. So if you want a default gateway, which you're going to need in the network at some point, it's the layer 3 IRB interface. That has to match between peers because you need the same Anycast IP address, and that's configured on the VLANs, where you configure a VLAN, point it to a layer 3 interface, i.e. the IRB, and you configure that IP address in the IRB interface. And then we've got something called redundancy group, or RG. This is again in the interface. There's a lot of configuration that actually goes into the interface. But really what this is down to, what this is all about the resiliency. So in the case that there is a failover, the redundancy group really defines, well, who's going to forward traffic. Those are the attributes that have to match, but when we look at the values that must not match, right here, highlighted in red for obvious reasons, you're going to have a local IP for ICCP that must not be the same as the remote IP. So if we look at MC Peer 1, that will have one IP address. MC Peer 2 will have a different IP address. They must not match for obvious reasons. If they are the same, it's never ever going to work. And the chassis identifier, again, this must not match. This is on the interface configuration. And what this does, this is so confusing, a local identifier that distinguishes the two physical switches inside an esi-lag peer. Wow. Right, okay, let's start with the configuration. On the left hand side of the display is the lab itself. On the right hand side is the secure CRT I SSH'd into the devices where I'm going to do the Junos configuration. I'll try and take this as slow as possible. I know I talk fast, and apologies for that, but I try to keep my videos as short as possible, but they always end up being really long for some reason, so I don't know. But I'm on MC Peer 1, let's start there. So let's go to the command line interface into configure mode. Now what you can see is that there are 3 aggregated Ethernet interfaces, AE bundles, on each of MC Peer 1 and MC Peer 2. There's AE0, AE1 and AE2. So what you have to do in Junos, do not forget this, is set chassis aggregated Ethernet devices, Ethernet device count. I had to remember it there. I thought it was just count, and we need to say 3. So 3 being I want 3 AE bundles. Now what we can see is that gig E0 and gig E1 are part of 802.3 AE0. So let's do that first. Set interfaces gig E000, and we do ether options 802.3 AE0, and I can now do the same for gig E001. And let's also do set interfaces gig E002 ether options 802.3 AE1, which goes to access 1, and set interfaces gig E003 ether options 802.3 AE2, which goes to access 2. Now at this point I'm also going to define and configure the aggregated Ethernet AE0, which carries the ICL traffic as well, ICCP traffic, as well as any data plane forwarding. So let's just do set interfaces AE0.0 for unit 0, family Ethernet switching interface mode trunk VLAN members, and I'm going to give the name ICCP as well as VLAN 10. And let's also now define those VLANs, because I've defined them but as part of the AE0 trunk, but there's no VLANs whatsoever configured. This is a blank canvas. So let's do set VLANs ICCP, VLAN ID, we could see it's VLAN 6, and let's also do set VLANs v10 VLAN ID 10, and there we go. So that is the initial configuration. We're by far not done yet. Now what we also have to do is define the ICL. We know the ICL is going to be AE0, but where do you actually configure this? So what you have to do is set multi-chassis, and then we have to point it to the esi-lag question mark. Oh, sorry, it's multi-chassis protection, and then it should be peer IP address. Now that is going to be 10.10.10.2 on MC peer 2, and we can now say it's going out of interface AE0. And now that we've defined what the ICL is, this multi-chassis protection, that is the ICL link going to the remote peer 10.10.10.2, which is MC peer 2, out of interface AE0. But we now have to configure the ICCP. Where do you do this? You go to Edit Protocols ICCP. And what we do now is define what the local IP address. So this is going to be 10.10.10.1. I'm also going to do set session establishment time, and I'm just going to do this for 5 seconds. I think it's seconds. Yeah, 5 seconds. Oh, 45 is the minimum, so let's do that. And now we're going to define what the peer IP address is. So let's do set peer 10.10.10.2. And now interestingly, if we do redundancy group ID list, this is going to be all the redundancy groups that we configure on the interfaces themselves. So where you can see there's MCAE2, that's going to be redundancy group ID 2, and where there's MCAE1, that's going to be redundancy group ID 1. So I'm going to do 1 and 2 here. Now if I hit question mark, you can also see we can do some liveness detection. This is basically BFD. So let's do liveness detection, minimal interval. I'm going to do 1000 milliseconds, I think that is, with the multiplier of 4, just random value. And if I do show, we can now see we've got our local IP address here, and we're peering to, or we want to peer to 10.10.10.2. Now the question is where is this 10.10.10.1 actually coming from? Because if I do top show interfaces, you can see minus the interfaces I've just configured, there's nothing there for 10.10.10.1. Now in this lab, this could be a loopback 0 interface, but I'm actually going to use an IRB interface. So let's do top set interfaces IRB.6. family inet address 10.10.10.1, and because that is using VLAN 6, if I do top show VLANs, we need to point the way for the ICCP VLAN to use this IRB interface. That's very simple. Let's do top set VLANs ICCP layer 3 interface IRB.6. Oh, this is a lot, isn't it? I told you it's it's a good setup. Okay, so if I now go to the top, let's just do a quick show compare to see what I'm pushing. So we've got the chassis to enable up to 3 aggregated Ethernet bundles. We've got our interfaces pointing towards those different bundles. We've got AE0, which is the ICL, really carrying the ICCP VLAN and VLAN 10 when we configure those interfaces. We've also got IRB.6, which if we go down to the VLANs is the layer 3 interface for the ICCP VLAN, and then we enabled the ICL via this configuration here, and then we've configured ICCP. So if I do a commit on this now, and that's passed, if I now go over to MC peer 2, and let's do the same, let's go configure a little bit quicker, set switch options, aggregate Ethernet. I forgot, I always get mixed up. Set chassis aggregated Ethernet, device count 3, and now let's do the same with those interfaces. Let's do set interfaces GIGI000, ether options 82.3 AE0, the same for GIGI001, and let's do set interfaces GIGI002 to access 1, 802.3 AE1 and set interfaces gigi 003 ether options 802.3 AE2. And now let's do set interfaces AE0.0 family Ethernet switching interface mode trunk VLAN members. Let's open the brackets up, ICCP and VLAN 10 or V10 for short. So let's now define the VLANs. Let's do set VLANs, not VLANs group, but V10 VLAN ID 10, set VLANs ICCP, VLAN ID 6, I think it is, yes it is, with the layer 3 interface IRB.6, and let's do set interfaces IRB.6 family INET address 10.10.10.2. Okay, we're getting there. And now let's go into edit protocols ICCP. Let's do set the local IP address of 10.10.10.2. Set the session establishment hold time of 45 seconds. Just want to confirm that on here. Yeah, it is, because don't forget, if that does not match the MC peering, the MC peering will not come up. And now let's do set the remote, or is it the peer IP address of 10.10.10.2. Let's do the redundancy group ID list. Again, that will be configured on the interfaces 1 and 2. Let's do liveness detection for BFD. So let's do minimal interval 1000, I think it was, with the multiplier of 4. Okay, and let's now also define, we can't forget this part, let's also define the set multi-chassis protection, and we define the peer IP address, so 10.10.10.1 as MC peer 1's, the IRB interface on MC peer 1, and that's going out of interface AE0. Let's do a quick show compare, and it pretty much looks the same, minus a few changes, a few things have been swapped around. But if I commit this configuration, fingers crossed, oh hang on, the peer IP must match with ones defined at so what's going on here? Peer, so I got that wrong. I didn't spot that, and oh, I love it, I love it. So let's do set protocols ISBP, and let's do set peer 10.10.10.1 redundancy group ID list. I'm just going to do all that all again. Liveness detection, minimal interval 1000, multiplier of 4. And let's do show. Yeah, I thought that there would be two different peers, so let's delete peer 10.2, and there should now be fine. So yeah, my local is 10.2, my peer is 10.1, top, commit. Hopefully that succeeds, and hopefully, fingers crossed again, the ICCP does come up. How can you verify that? Just do run show ICCP brief, and we can see it's in progress. It does take a few seconds, and now you can see it's finally established. I did have to do some troubleshooting there. One point to mention is that if I do show interfaces IRB.6, I changed it from a /32 to a /24. The IRB interfaces, the addressing for ICCP has to be in the same broadcast domain. I missed out the /24 at the end. Junos automatically defaults that to a /32. I changed that. So now we have, the good news is that it is established. And if I go over to this guy here and do the same, run show ICCP brief, you can see it's established for these different redundancy groups. But if I come just down to user 2, for example, and let's ping the user 1's IP address of 192.168.10.11, it's not going to work. Even though access 1 and access 2 are perfectly configured, they're ready to go, we haven't configured the AE bundles, the MC AE bundles, AE1 and AE2, from these MC peers to access 1 and access 2 respectively. So that's the next step. So really all we've done so far is we've just enabled ICCP. That's all we've done. We've now made MC peer 1 and MC peer 2 to appear as the same logical upstream device, but those interfaces to those downstream devices are not configured yet. That is the next step. So what we can see from this MCP peering MC peer 1 and MC peer 2 is that we need to configure AE1 with multi-chassis aggregated Ethernet 1 going to access 1. So let's do set interfaces GigE002, and that's ether options 8.3 AE1. I'm going to do the same for the GigE3 whilst I'm here, but that's going to AE2 to access 2. And now let's edit interfaces AE1. Now, if you recall, LACP comes in quite a lot when it comes to ICCP and bringing esi-lag up. So the first thing I'm going to do is set aggregated Ethernet options LACP system identifier. This is that 6-byte hex value. This tricks the downstream device into thinking it's connected to the same upstream device. So this has to match between every peer when it's going to the same end client. So I'm going to do 00, 00, 00, 00, 00, 00, and I think that's enough, 01. And let's do the same, set aggregated Ethernet options, LACP admin key. This is to authenticate the control plane. So I'm going to keep it simple and do admin key 1 for MCAE1, just so everything makes sense. And I'm also going to do set aggregated Ethernet options, LACP, and I'm going to set this to actively send out those LACP BPDUs. Now we're going to get into a bit more of the multi-chassis aggregated Ethernet options. So we have to do set aggregated Ethernet options MCAE, and now we're going to give the ID of this MCAE bundle. So I'm going to give it ID of 1, hit up and hit back. I'm now going to give it a chassis ID. I'm going to give this a chassis ID. It's either 0 or 1, so I'm going to give this an ID of 0. Next is the redundancy group. So I'm going to give this a redundancy group number of 1. If I do top show protocols ICCP, you can see that we listed, or I configured, a redundancy group list to have the redundancy groups 1 and 2. And that's where this is coming in here. We're linking this redundancy group 1 for this interface into this ICCP session in this routing instance with this service ID. But we also need to define MCAE, the mode. Now this is either going to be active active or active standby. I'm going to do active active for multi-tenancy and everything's up as such. But when you do mode active active, you also have to do the status, I think is status control, and one has to be active, one has to be standby, i.e. MCP1 can either be active or standby, and MCP2 has to be the opposite. So if peer 1 is the active, peer 2 has to be the standby. And it's recommended to keep them the same for the different MC bundles on the same switch. I know it's complex, but let's do active here. And let's do a quick show, and that's looking, so yeah, it's looking pretty good. But this is just the aggregated ether options for LACP and MCAE. That's not, we haven't configured the trunk yet, so we have to do set unit 0 family Ethernet switching interface mode trunk, and we want to trunk VLAN members V10. And with that configured, let's now go over to MC peer 2 and let's do exactly the same. So let's just do set interfaces GigE002 ether options 8.3 AE1 to access switch 1. Let's also do the same for the AE bundle going to access 2, which is AE2, and now let's go into edit interfaces AE1. Now let's do set aggregated Ethernet options LACP active. We want to send out actively those LACP messages, and let's do set aggregated Ethernet options LACP the system identifier. Again, this has to match between peers going down to the same end device. 0, 1 there for MCAE1. Just so it's all consistent. And let's also do set LACP, admin ID key, 1 there, do show, and you can see it's starting to look the same. But we've now also got to do the MCAE, so let's do the MCAE ID of 1, hit back, let's do the redundancy group of 1, let's also now do the mode of active, active, and because MCP1 was active in the status control, this needs to be passive, I think it is, or standby. And now let's do show. You can already tell it, say it's saying, yeah, you're missing the chassis ID. That's fine. I was going to do that next. But let's do that now. Set MCAE chassis ID of 1. Okay, so let's do a show on that. So what we've got here under LACP is everything will be the same. The system ID, the admin the system ID, the admin key, and the mode will be the same as MC Peer 1. You can see it's exactly the same there. There's only slight differences in the MCAE bundle, and that is really between the status control and the chassis ID. So we've got a chassis ID of 0 here, and the status control is active on Peer 1, but on Peer 2 the chassis ID is 1 and the status control is standby. That is the MCAE 1 configured, but we need to do the same for MCAE 2, which is pointing down to access switch 2 and inevitably the user 2 as well. So let's just do top edit interfaces AE2, do exactly the same, active for the LACP, system identifier 000000000002 this time, and let's do LACP admin ID key. I'm going to give this a key of 2 now. Again, these have to match between different peers, but they have to be different between different MC bundles on the same switch. I know, it's complicated, right? And now let's do MCAE. The MCAE ID is going to be 2. Chassis ID is going to be 0 to keep it consistent. The redundancy group number is going to be 2. The mode is also going to be active. And the status control, to keep it consistent, is going to be active as well. So let's do show, and you can see it's almost there, but we cannot forget to do the set unit 0 family Ethernet switching interface mode trunk VLAN members V10. So if I go up and do show AE, didn't think that would work, but let's just do show. Could have done a wild card, but we've got our ICL link. We know ICCP is operational. We've got AE1 here, and just below we've got AE2. Now I'm just going to go over to MCP 2 and do the same, and let's do set aggregated Ethernet options LACP active, system identifier 000000, practically really the same, or it is the same, and let's also do the admin key of 2, and now let's do the MCAE configuration. So we will want redundancy group 2, we want the chassis ID of 1, we also want the mode of active, and to keep it consistent we need the status control on this one to be standby. I know I'm forgetting something. Is that it? Let's have a look. So we've got MCAD. Let's go over to MCP 1. I'm having to double check this because there's a lot to configure. That actually looks like that's it for the MCAE configurations. But unit 0 family Ethernet switching interface mode trunk VLAN members V10. I've done something wrong here, haven't I? I've just realised I'm in AE1. I swear I'd done. Okay, so I'm going to have to change that. So let's change that back. Okay, let's get it right this time. I've just changed it, as you can changed it back. So let's do top edit interfaces AE2, and let's do show. Yeah, there's nothing there. I must have mistyped that. So let's do set aggregated Ethernet options LACP active, system identifier. Now that I know for sure I'm in the right one, that system identifier once again 02 at the end, and let's also do the admin key of 2, set MCAE ID 2, we're going to do the redundancy group of 2, going to do the chassis ID to keep it consistent of 1, mode is again going to be active, and the status control is going to be standby here. So let's just go up and let's just do show just to compare AE1 to AE2. So we've got AE1 here looking good, and we've got AE2 here without the trunk information. I swear I just done that. Am I going nuts? So let's do set AE2 family Ethernet switching interface mode trunk VLAN members V10. Okay, now I know that should be there now. If it's not, I don't know what is going on. But here we go. So that is everything there for AE1. Everything looks correct for AE2. If I come across onto MCP1, we can see it all looks the same, minus the subtle differences that have to not match between peers, but also have to be different between different MC bundles on the same switch. And AE2 here. Okay, at this point this should work. So let's just go to the top. Let's do a quick commit check on both of these devices. Commit check, and peer 1 is saying it succeeds. Let's commit that. Let's commit the configuration over on peer 2 as well. Fingers crossed, peer 1 should be, host 1 should be able to ping host 2. But let's actually just do something first. Let's just do a run show ICCP brief. We can see both of these are up, but that's just over the ICL with the ICCP protocol. There's really not much ICCP configuration viewing what we can do in terms of troubleshooting. It is quite limited. The best way at this stage is just to test connectivity. So let's go on to user 1 and let's ping 192.168.10.11. Let's just make sure it has got an IP address. It has. Can it ping the user 2 at the bottom of the network? Fingers crossed. And there we go. So we know that switching is there. So there we go, everybody. That is esi-lag. That is what it is. What benefits does it bring? What challenges does it bring? And from a lab perspective, how to configure esi-lag in Juniper Junos. I did say I was going to give my summary and thoughts on whether to esi-lag or to not esi-lag at the end. Honestly, I think there are much better protocols out there. I think there are much better ways of giving network resiliency, network redundancy, and loop-free prevention techniques, etc., etc., without the complexities of esi-lag. Yes, it does what it says it will do, but there are so many things to go wrong. I was just in a simple lab, as you saw, getting things wrong because you're constantly having to check and validate. This has to match on both devices, but this cannot match between different devices, between different peers. But then if it does have to match between the peers, it can't match between different MC bundles on the same switch. But then also take into account, then you might have different routing instances, so on and so forth. It is actually quite complicated to configure. And I'm sure there was a lot more that I could have done in the esi-lag configuration. So my general thoughts, my summary is to not esi-lag. That is my suggestion. Take it as it will. If you are going to deploy esi-lag into your network, please read documentation. Please refer to vendors' documentation and best practices, etc. But certainly from the experience you've just seen, it's complicated. You can get things very easily wrong, and I know, and this will be the next video, that things with esi-lag just do the same thing but in a much cleaner, nicer way. So that's it for this video. As always, I do thank you for watching. Thank you for your time and for your support. If you like this video, if you like my content, please give it a thumbs up. It's the best way to support my channel. Any questions or comments, let me know down in the comments box. I always love hearing from you all. Other than that, thank you for watching and goodbye.